Today we are going to be covering vectors, linear algebra, introduction to linear algebra. Vectors are basically some of the most useful things that you're going to come across from a from a point of view of like dealing with data, from a point of view of just dealing with identifying structures in data, right? So the whole field of linear algebra deals with manipulating vectors. It deals with it basically like linear algebra literally means like algebra of linear systems. That's what linear algebra deals with, and typically linear systems are something where you have a change. So when you have a change in quantity x, that change is linear in quantity y, right? So the basic principle is that if you have y it's equal to mx, right? Where m is some number, some weight factor, and then x is the value that's changing, right? So in terms of as a field, linear algebra is like vast because you can do all sorts of manipulations for when it comes to data. You can do all sorts of amazing things with it. But what we're going to focus on are some of the most sort of fundamental things, right? We're gonna really start from the very basics. We're gonna start with like scalars and vectors, and then we're gonna move on to more complex ideas. Yeah. So basically, what we're gonna be talking about today first is vectors. So scalars and vectors. And I'll kind of give you the context of why we care about vectors when it comes to data, right? And like before I do that, I'll introduce vectors to a little bit, to some extent, and then I'll do that, right? So let's first talk about like what are scalars and what are vectors. So a scalar basically is just a single number, okay? So if I write the number 2, I consider that a scalar, okay? Well, I write the number 100, I consider that a scalar, right? I write some quantity x, I consider that a scalar, okay? Or I write some quantity y, I consider that a scalar, okay? That's what it is. Very straightforward, okay? Nothing fancy about that. So a vector is a little more complex. So to define what a vector is, so a vector simply is just a pair of numbers, okay? So if I have 2, 3, it's considered a vector, okay? It's a pair of numbers that goes everywhere together. But there's actually a really strong geometric interpretation to this, okay? And that strong geometric interpretation is super useful to understand because it helps us, it helps us give us perspective about like what's here, right? So when we say 2, 3, what we're talking about in terms of a vector is not just numbers. There's a specific structure associated with it. So if I take an x and y axis, okay. Oops. So suppose, so this is my x-axis, this is my y-axis, and this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's make these numbers a little bigger. Let's make them 4 and 5, okay, 6 and so on, right? And then this is so on. So my value of x is 4, and my value of y is 5, okay? So that's what my vector represents. So my value of x is, so it's here, right? So I actually have this line that I'm drawing from, so this is 4 units long, that's the number 4, and then this is 5 units high, that's the number 5, right? So basically a vector is nothing more than this object here, okay? This object called v, okay? So I would call this as vector v, Okay, so basically what's happening is I'm taking, on my two-dimensional coordinate system, right? On this two-dimensional coordinate system, I'm taking 4 steps to the right, and then I'm going up 5 steps. Okay, so when I go to that specific point, which is this point, I'm basically drawing an arrow from the center, okay, from the center 0, 0 all the way to that point. That's basically a vector. Okay, so the core idea of a vector is that it has a direction. You know, there's some directionality to it, right? So in this case, that direction is given by how many steps you take to the right and how many steps to the you take to the left. Okay, that's what the directionality is given by. And the idea is that it also has a magnitude. Okay, so we say usually that a vector v has direction and magnitude. So what is the magnitude? So the magnitude essentially is the length of the vector. Okay, so the length of the vector essentially tells you, like, it basically, it's just one number that quantifies like what is the length of the vector. Okay, so the magnitude is a single number. Okay, it's a scalar. Okay, and the direction essentially is given by these 2 numbers, right? So the direction essentially is given by those 2 numbers. It's basically the direction it's pointing. So when you throw a ball in the air, right? So how do you know that its position has changed, right? So when you throw a ball in the air, like, how do you know its position has changed, right? You put it on a 2D grid, right? You do X and Y, and you say this is one point, this is another point, right? So how you actually measure that change is you draw a vector for both these points, and then you look at the difference of those vectors. Okay, so if this vector here is v1, and then if this vector here is v2, what I would do is v2 minus v1, and that is the difference. And this is how much I've traveled from the point that's defined by v1 to the point that's defined by v2. Okay, so that is the distance that I've traveled. Okay, and it also gives you the direction that you've traveled, right? Starting from one point to another, right? So that's sort of the notion of a vector, right? So and to understand the notion of a vector, you have to understand the idea of a dimension. Okay, so you know, a dimension is nothing more than like the direction that you're moving in, right? So you have the x direction, you have the y direction, you have the z direction, right? So this is an example of a 2D vector. Okay, this is an example of a 2D vector. You can have vectors in 3D. Okay, you can have vectors in 3D, right? So you can have something like this. This is going to be tough for me to draw. Don't mind. I'm not a very good artist. So I can have a vector like this, right? Where what's actually happening is that, you know, I'm starting. So okay, let me just place this from here. So I have, you know, so I am going, so this is the point I'm at. So let me just project it down. So, and then I have the height, right? So these are the three different coordinate systems. So I have X, I have Y, and I have Z, right? So this is my vector in 3 dimensions. Okay, so let me just call this V3 because this is like vector in 2 dimensions. This is a vector in 3 dimensions, right? So because like even in 3 dimensions, right? Just think of the world around you. you can move in 3 dimensions, right? So there is a sense of direction, right? And there's a sense of sort of motion, like, okay, I can move in various directions. And, basically the vector essentially is just telling you like which direction you're pointing at, right? So I can be pointing either in this direction, I can be pointing in this direction, I can be pointing up, down, right, left, right? So the vector is kind of like a guide of sorts, telling you which direction you're pointing in, right? So now comes sort of the first question. Can you have a vector in 1 dimension? So, okay, so what would 1 dimension look like, firstly? Anyone want to hazard a guess? So the question is, so we spoke about 2D, right? We spoke about 3D. How would 1D look like?
A straight line.
Straight line, right? And can you talk about direction in 1D? Anyone hazard a guess? It doesn't have to be correct, just hazard a guess. Think about it, that's all.
Yes, you can have direction.
You can have direction, right? So why do you feel you can have direction?
Well, for example, if you're indicating north, it's a straight line showing north direction.
So you're correct, but how would you state it, right? So here we were talking about taking steps in the x direction, taking steps in the y direction, right? So so basically the answer is that here you have the notion of taking steps, right, in 1 dimension or the one direction or the other, right? So you are either taking steps to the right or you're taking steps to the left, right? And that's why you have this notion of directions, right? So you can take steps in either direction. So a 2D vector would look like, say, 3 or 4, like that would be a 2D vector. A 3D vector would look like this. Those numbers can be misleading. 5, 6, 9. And a 1D vector would just look like 10 or minus 10. So notice that it's a single number, right? But it doesn't. So the thing is that mathematically speaking, it doesn't behave like a vector, but it kind of does have that notion of direction, right? And the direction in many ways is the magnitude. Okay. In these cases, the direction is not the magnitude. I mean, the direction is actually given by the sign, right? So which direction you're going, whether you're going to the right or whether you're going to the left, is given by the sign, right? So if this is 0, if you're taking 10 steps to the right, you're gonna have like positive 10, right? And if you're gonna take 10 steps to the left, you're gonna have like negative 10. So it could be that you're taking like you're starting at 0, and then you've taken like 10 steps to the right, right? So you've done those 10 steps, you're here, and then you decide to move back, right? So you decide to move back like a few steps, then initially like you've taken 10 steps, and your x is at that, and then your first x point is that, and your second x point is essentially at 5, right? So in which case your delta x, right? What is the change, which is x2 minus x1? That's going to be negative 5, right? Because you have actually like gone down, right? So you were at a higher, you were at a farther away point and you've gone down, right? And that same logic applies to any dimension, right? So remember, like having 2 dimensions is nothing more than like having 2 of these 1 dimensions, right? So this idea of sort of moving in 1 direction and then moving in the other direction, that applies also in 2 directions, in 2 dimensions and 3 dimensions, right? So this is sort of the general idea of a vector. So the other thing I should probably cover is magnitude, right? So the magnitude of a vector So if this is your vector v, right? And if this is my point xy, and this is my point 0, 0, okay? And this is my x, this is my y. So the magnitude, we say that the magnitude of the vector is nothing more than, so it's actually done, okay, let me do it like this. So let me call this x1, y1, okay? So essentially, or x2, y2, and we'll call this x1, y1, okay? So the magnitude of a vector is essentially this quantity, okay? Okay, so this quantity, you know, it looks messy, but it's actually fairly straightforward. So all it's telling you is that I want the difference between the x's, okay? So x2 minus x1, which is this difference, okay? So my x2 here is some number, and then my x1 here is some number. So I care about like this this difference, okay? And then I care about this difference, okay? y2 minus y1, which is what this is, okay? And then x2 minus x1 is just this, right? And then essentially what I'm doing is this is how you calculate the hypotenuse of a triangle. Like you would have done this in school, which is literally just like you have a, b, c, right? So c squared is equal to a squared plus b squared. That's all it is, okay? And then c is equal to square root of a squared plus b squared, okay? This is just basic geometry. That's all this is. So when you write this notation down here, right, with these bars and this vector symbol, so whenever you have a vector, you put this little hat. What you're basically doing is just calculating what is this length here, okay? So this whole operation lets you calculate the length. Is this part clear? Any questions on this? So I'll give you sort of more examples here, because this part is super crucial as we go along, right? So in this case, right, when I calculate v, what, so can somebody tell me, given x1 and y1, right, what's going to happen to this term here? Like what do I write here? So you know what x1 is, you know what y1 is. So what would I write here? So, you know, let me start with saying that there's a square root, and then what are the other terms that I have to write next?
y2 squared plus x2 squared.
Yep. Does that make sense to everyone? And please stop me and say like if it doesn't make sense, right? Because so what I'm essentially doing is, because y1 and x1 are 0, we are just looking at, you know, y2 squared plus x2 squared, which gives me which gives me this quantity, which is the length, right? So when you talk about a vector, essentially it has length and it has direction, okay? The length is given by this magnitude, and the direction is given by the sign of your vector, okay? So if you, so let's work through some examples here, okay? So if I give you let's work through, okay, we're gonna generate a 2D grid here, and then we're gonna say, so this is x, this is y. So if I give you a vector 0, 1, right, and this is x, this is y, How would I draw this vector? So let me say 1, 2, 3, 4, 5. 1, 2, 3. Okay. How would I draw this?
So X is gonna be at 0.
Okay.
And 1 is at Y.
Okay. So X is going to be at 0 and Y 1 is at Y, right?
Yeah.
That's that vector, right?
Yes.
So
Mhm.
let's just suppose, okay, so let's just do this. What will it look like now?
From X is at -1,
So where is -1?
the opposite of 1.
Will it be here?
Yes.
Nope, it'll be here, right?
Oh, yeah, yeah. I mean, yes.
This is -2, this is -3,
Mhm.
-4, -5, right? So your second point is it'll be here. There'll be -1 for X and then 1 for Y, right? So,
Yeah.
so our vector is going to look like this, right? That's how it's going to look like. Suppose I do, you know, -2, -5. Can anyone help me figure out like how it'll look like? -2, -5. So X is -2, right? So X is -2 is here. Where's -5? So this is -1, -2, -3, -4, and then -5, right? So it's here. So that's my vector, right? Does that make sense? Any questions on what we did so far?
So is the point your vector or the whole line?
The whole line. The whole line is a vector. Okay. So this whole, yeah, so that's a good point. Is the point my vector or the whole line? The whole line is the vector. Okay. So when you think about vectors, you know, the point is the coordinates of the point, the signs of the point are giving you the direction, and these values, when you calculate the magnitude, are giving you the magnitude, right? The length of the vector. When you calculate the magnitude, they're giving you the length of the vector. Okay. Does that help? Rebecca,
Yes,
were you the
that's
one who asked?
helpful.
Yeah.
Yeah,
Okay.
that's helpful.
So,
Thank you.
Yeah. So basically, remember the sign, you know, minus or plus gives you direction, and then the numbers let you calculate basically the magnitude or the length. Okay. So there's another actually like sort of interesting way of thinking about it, right? So let's take a vector that's like this. Okay. So if you look at this vector, right? So what are the coordinates of this vector? So this is like 4. So this is 4, 4, right? So the thing is, I actually don't need so when it comes to the length, right? I need the 4, 4, right? Because I need those numbers. But when it comes to direction, I don't actually need the entire vector, right? So if my vector is 4, 4, okay, or let me write it in proper notation, 4, 4, I can just divide it by 4, right? And I'm gonna get 1, 1, and the 1, 1 is more than enough to tell me what is the actual direction, right? I don't need the entire, the entire vector, okay? So I just need the 1, 1 to tell me like what is the dimension, right? Or direction, sorry, right? So when you look at the magnitude of the 1, 1, right? So what is the magnitude of 1, 1? It's just 1 square, 1 square, it's root of 2, right? So so usually like so actually in this case it wouldn't be 1, 1. It would be a different set of numbers, okay? It wouldn't be 1, 1. It'd be some other. I'm going to explain this notation, x hat, y hat, because what that x hat, y hat would do is the magnitude of so this number wouldn't necessarily be divided by 4. It'd be divided by some. It would be divided by some number. Okay. So what this x hat, y hat would do is it would make sure that the magnitude that I get is equal to 1. Okay. So the length of this vector would be equal to 1, and the x and y essentially would be values which tell you what is the direction that it's pointing. Okay, so so when you do your y square hat plus x square hat, it would essentially give you 1. Okay, so there's a way that you can calculate, like you can calculate you can calculate these y hat and x hat. I'm not going to go into that, but this idea here is that of a unit vector. Okay, this basically tells you that you're pointing in the direction of this vector v, but you're doing so like the smaller vector essentially is just telling you that is the direction it's pointing. The magnitude is just 1. Okay, it's not, it's not whatever is the magnitude of v, right? And the idea of a unit vector is extremely useful when you're thinking about vectors, because when you look at vectors, you can have like so you can have a vector of any kind, right? So here we have a unit vector of 1, that you have the line that is defined by that unit vector, and you can have a vector of any size, right? I can have a vector of this size, I can have a vector of this size, right? It's all the same, right? Like you can have like multiple vectors, but they're all pointing in the same direction as the unit vector that we have, right? So they're all pointing in the same direction as this vector here, right? The blue guy. Usually people denote that with like a little hat. Okay, we call it unit vector v. So this hat notation is a little bit iffy because it's also used in machine learning for a different purpose. So don't get married to that notation. But the basic idea is that the unit vector essentially is telling you what is the direction the vector is pointing in, right? It's giving you that information while it's making sure that you don't care so much about the length, right? Because if I have a vector that's really long, I can't really plot it, but I just want to visualize it, so I know what the magnitude is. I just care about the direction. Sometimes when you're looking at doing vector calculations, you only care about directions. So in that case, it's just good to have an idea of like what is the direction of my point, So I can just calculate these unit vectors. It'll just tell me this is the direction of this point. So suppose I have a grid where I just want to know like what is the direction of these 2 points. So just calculate a unit vector in this way, and now I know, right? So I don't need any other information about these points once I calculate the unit vector. Okay, so I mean that's just like it's a bit of an aside, but it's a useful aside to keep in mind when you're thinking about vectors and directions. So this is one thing. So everything up till this part is clear, right? You guys understand the notion of a vector having a length and a direction. Okay, looks like everybody understood. All right. So far we looked at 1 dimension. We looked at 2 dimensions. We looked at 3 dimensions, right? So does everyone agree that you can have vectors in 2 dimensions, you can have vectors in 3 dimensions, and in 1 dimension? Actually, I mean, the vector in 1 dimension isn't truly a vector. So let's ignore 1 dimension for now. So let's talk about 2 dimensions, right? So in 2 dimensions, you have a vector. In 3 dimensions, you have a vector, right? So that makes sense, right? So what about 4 dimensions? Can you have a vector in 4 dimensions?
Yes,
Okay, yes. How do you draw 4 dimensions?
with an extra point.
An extra, this in which direction? Can
Not
somebody
sure.
draw me? Okay, you're not sure. Others? Anybody? So my question is, what about the rest of the dimensions? 4 dimensions, 5 dimensions, 6 dimensions, and so on. Can you draw any of these? Come on, you people are super smart. You guys should be able to draw dimensions. It's just drawing. Chernia, are you there? No. Okay. So the answer to this is you can't draw it. You can't draw it on a piece of paper, because a piece of paper like this is a 2-dimensional surface, right? So the maximum you can reach on a piece of paper is 2 dimensions, 3 dimensions, right? But even in 3 dimensions, you cannot draw something that's 4-dimensional. Okay, because we humans only perceive things in 3 dimensions. We do not have so any information out there in the world, right? Whether it be moving objects, sights, sounds, anything, we have to perceive it in 3 dimensions. Like it's beyond, like we cannot perceive anything beyond that, right? I mean, the only other dimension that we know of is time, and time is not a vector quantity. Okay, so time is more like a 1D thing, and in time you're just moving forward. There's no moving backward, as far as we know, as of right now. So so the idea is that, you know, we visualize the world in 3 dimensions, and we understand the world in 3 dimensions, right? And those are our 3 spatial dimensions, like X, Y, Z, right? But when it comes to data, right? Data, there is no restriction that it has to be only 3-dimensional, right? Data can be it can be of any dimensions, right? You can have data that's 5-dimensional, 10-dimensional, 15-dimensional, and so on, right? So that's, you know, that can be, it can exist in as many dimensions as you can imagine, right? And you can have like an infinite dimensional situation as well. So you might be wondering, okay, like we talked about like X, Y, Z directions, but how can you talk about dimensions for data, right? So the simple idea is when somebody gives you a data set, right? When somebody gives you a data set, okay, I'm just gonna sit down for a second so you might see me disappear on the screen. Okay, so when somebody gives you a data set, you're gonna have rows and columns, right? So suppose I give you a data set where I have, you know, row 1, 2, 3, 4, 5. I have column 1, 2, 3. Okay, so what we can do is we can say that these columns are actually like column 1, 2, 3 are actually dimensions. Okay, so we basically say that, oops, you know, column 1, oops, so column 1, this is column 2, column 3. Okay, so let me simplify by just taking 2 columns. Okay, and then I'll add the 3rd column. So essentially we say that the rows and the columns, so out of that, the columns are like exactly like dimensions, right? And each row is like one data point in that, right? So so for both columns, so for both column 1 and 2, I'll have, you know, some x1, y1, x2, y2, x3, y3, or, you know, rather than, yeah, so okay, for now, like, let's just go with like, yeah, so I'm gonna have x1, y1, right? So this is gonna be my 1 point. It'll be x2, y2, it'll be some other point, some other point, some other point, some other point. So those are my 5 points, right? So I have my 5 rows of data. So each point here corresponds to 1 row of data.
Yes.
Yes. Okay. So now I can have in a data set multiple columns, right? So I can have, you know, 100 columns in a data set, right? So what I essentially have is a 100-dimensional space, right? So we call this a space. So when I define like column 1 and 2, we call it like a column 1, column 2 space, right? Because your collection of points is defined by this space of sorts, right? Which is x and y, right? So that's a space. So you can have 100 dimensions and you'll have a 100-dimensional space. So we usually say that this is a 100-dimensional. Yeah, so I can have as many columns as possible, right? So the other thing is, so when you talk about like, so let's simplify this and let's take like a 10-dimensional space, right? So in my data set, I would essentially have call 1, call 2, all the way to call 10, right? And then I have row number 1, 2, 3, 4, all the way to say 100, you know, points, right? So essentially, right, what I have here is a vector. Okay, so each point in that space, in that 10-dimensional space, is a vector, which means that I actually have, so the first point, the first row of data, okay, is essentially my, so usually in this notation, in this situation, we use a notation x1, x2, all the way till x10, okay, because that's what it is. So this is the same thing, or this is equivalent of saying, you know, so for the first row, for row 1, you have column 1, column 2 value, column 3 value, all the way till column 10 value. Okay, so this is all the set of points here. Okay, which I've just arranged vertically. Those set of points here. So those set of points are everything it for row 2 here. Okay, so we would say, strictly speaking, the way we would write this is, so this would again be like x1, x2, all the way till x10. But usually what we do is we attach a number on top here. So, I mean, people can change this notation, but this tells you the row number. And this tells you the column number. So that's one way to represent it. But basically, that's what. So this is why we care about vectors, because we can represent data sets as points in space, and that space essentially is defined by the columns that you have, right? In a data set. And any questions with this? Yes, no, made perfect sense. So I'll show you guys an example of this, right? Like, let's look at a real data set. Okay. Oh, where did my real data set go? Okay. So let's look at this, right? So this is a real data set. So I've imported something called the California housing data set. Okay. I've fetched the data. I have the data dictionary, right? And I've pulled. So let me go over this line by line. It's just easier. So Python actually gives you like mock data set or toy data sets. Okay. So if you go to sklearn is a library in Python, and you do sklearn.datasets, you can actually fetch a lot of toy data sets. I think there's like 7, 8 of these data sets, which are like toy data sets. Okay. And I'm just importing pandas. This is like fairly straightforward. And I'm fetching the California data set. So the California data set is actually a data dictionary. Okay. Well, it's a specific type, but basically it behaves like a dictionary. Okay. So there's a description. There's feature names. There's target. We'll not worry about target so much right now. We'll define that later. And then we have the data. Okay. So what I've done here is I've pulled that data. Okay. And then I have essentially, so I've pulled that data and I've pulled the names of the features. Okay. And I'll talk about later why we call them features, because in machine learning, like, you have features and a target. Target is what you're trying to predict. Features are what you're trying to use to predict the target. So that's why they call it features. But for your usefulness at this moment, think of the features as just column names. Okay. And you'll see when you declare, when you put this into a pandas data frame, this is actually called columns, right? So when you look at this data set, you have columns and you have rows, right? So you have 20,000 rows and you have, 1, 2, 3, 4, 5, 6, 7, 8 columns, right? So each column is like a dimension, is a dimension, okay? And each row is like one data point. Okay, so in a 7-dimensional space, right, which is defined by these columns, you have each like this row is one data point. It's like one point that sits at a specific, it sits at a specific value. you have 0.2 that sits at another value, 0.3, 0.4, 0.5, like that. This thinking of it might seem trivial, but this is an important thing to understand, because once you understand like how, why are we doing like linear algebra, right? Like when there's all stuff you might have come across in high school, or you might have come across, in your undergrad or something like that. But all of it's important because when you start looking at data, right? So when you start thinking about data in terms of vectors, it becomes really easy to sort of, manipulate them and like, okay, so if I take one point, right, and I add a certain number to it, what's going to happen to it in that space? It's actually going to move, right? So, and like that's something that we'll do next. But the idea of visualizing, like, how do you visualize data, right? Like the idea of visualizing data as this this sort of cloud of points, this idea, like, so imagine if I just took three if I just took like 3 columns of data, right? I would essentially have a cloud of points in 3 dimensions, right? So if I had just median income, I would have had house age and average room. I would just have a cloud of points in 3 dimensions, right? And then as I add more dimensions, my cloud, like I have, I have the points, I have the same number of points, but I have more information because I have all these other dimensions, right? So that's sort of a weird idea to wrap your head around, but it's an extremely useful idea to wrap your head around. So that part is important. Okay. So the first part of this notebook essentially just deals with this, right? It deals with what the idea of a vector is. So when you look at like latitude and longitude, a position on a map, that's essentially also a vector, right? So when you use Google Maps, when you look at latitude and longitude, what you're basically, getting, like it's so latitude and longitude is a little more complicated because it's actually a vector, not on a plane surface, it's on a sphere. Okay. So the grid itself is on a 2D surface. So everything that I told you just now makes sense if I have a flat plane, right, like this. But if I give you an object like this, right? So I have a plane here, like I have a curvature here. So if I put that grid on here, then two lines that go straight on the grid are not going to go straight on the grid, right? They're going to meet at some point. So in a flat grid, if you have 2 lines which are going parallel, they'll always be parallel. Okay, they'll never touch each other. Okay, they'll always do that. But if I have a sphere, right, and if I shoot like 2 beams of light that are going straight, they will curve around and they'll meet at some point. Okay, that's because there's curvature in space, right? So latitude and longitude like that is a little complicated because it's not as simple as like you can just add things in a simple way. But if you just look at it locally, right? By locally I mean if you zoom into a map, right? It's pretty flat on that on the scale, on that distance. So if I take again like this object and I really zoom in closely, right? I go extremely close. What's going to happen is it's almost flat. So it behaves exactly like you're on a flat sheet of paper. Okay, so that's why it's okay to sort of add latitude and longitudes if you're doing something on a local level, but it's not okay to sort of add latitude and longitudes if you're doing it like at between continents, because doing any kind of additions between continents, because what tends to happen is that your curvature becomes important, right? So basically, like any kind of position on a map is an example of a vector, okay? Because you have magnitude, you have direction. So we have also designed this like simple little applet that you can play around with, but the basic idea is that here is a red point. You have basically this is your vector, this is your point. You can move it around, you can play around with it. And so I generate a second point. Interesting. I did not know that this thing could do that. This must be new. Okay, so something for you guys to play around with, right? So, and again, like we defined like the magnitude of vector. So let me just open this notebook. I don't know why the LaTeX is not rendering. Yes, I know this can be the maths part. The math parts are, you know, once you start getting a hang of it, once you do some stuff on your own, it makes a lot more sense. But you have to do stuff on your own. So what happened here? Oh, there's a bracket missing. Okay, so here, so this is what I was talking about, which is the magnitude formula, right? So when you go through this notebook and refactor, make sure you go through it. I didn't ask you to go through this notebook before coming to class because I know that this stuff can be a little bit complicated. So I just wanted to work through this first, so before you actually touch this stuff. So that's something to think about. Okay, and then here is the idea of a unit vector, which is essentially, can't move this point around. So you have these sort of 2 points. So you have the unit vector is essentially like this point where it's just pointing in the same direction, but the magnitude would change. So there's something wrong with this applet because this point should be moving around. I'll check that, but I think it should be fine. So then you have this. So this is like an example of a unit vector, right? So here you can see that the magnitude of the unit vector is 1. Okay, basically the length of the unit vector is 1, but I can just keep changing my direction, right? My x and y component will always, they'll essentially sum when you do the square and then the square root. When you do the square sum and then the square root, it should always equal 1. But the x and y components can change, right? So it can be any direction. Okay, so this vector orientation is just telling you like what angle it's at. Okay, the applet is a little slow, but so the core idea here is that you can essentially have, yeah, I mean you can essentially have a vector in any direction. Okay, and the magnitude will always be 1. That's the whole goal of a unit vector. Now, on top of this vector, you can superimpose any vector. So the next thing is like fairly trivial. Like there's the whole idea of vector addition and vector subtraction, right? So the idea of vector addition and vector subtraction is pretty straightforward. So the idea is, so suppose I have a vector like this. I have a vector like this, right? So I have v1, which is x1, x2. I'm going to call this x1 dimension and x2 dimension. So I'm just going to call this. So let me call this capital X and capital Y. So x1 and so x1 is, it's an element of the x1 dimension, x2 is an element of the x2 dimension, right? So I have another x1, x2 dash, okay? So the same thing, x1 dash is an element of, it's part of x1, okay? So what this symbol means is part of. So you can actually think of x1 as a set, okay? So this is where, like, you know, so think of like x1 as an infinite set of points, everything from 0 all the way to infinity, okay? Actually, everything from minus infinity to infinity, okay? So you can think of it like a set, okay? So when we say that x1 is an element of x1, what we're basically saying is that, think of, so remember, like when I was talking about last time, you can have a single element as a subset, right? So basically, x1 can be thought of as a subset of x. Okay, but usually what we say is that the single value, right? The single value of x1 is an element of this larger set, which is capital X1. Okay, so if you have this vector v1 and then you have this vector v2, right? So this is v1, this is v2. So you're gonna have a third vector, which is v3, which basically is going to be x1 plus x1 prime, x2 plus x2 prime. That's basically like what you're doing is you're adding the x components. So you're saying that I'm going to add this component, which belongs to x1, and this component, which belongs to x2. So the total length is this, right? This purple line, which is essentially a sum of the green line with the blue line, right? So that's all it is. Okay, that's all there is to it. And then the same applies for the y dimension, right? So so for the y dimension, it's again this purple vertical line, right? So if you look at like v2, so what is v2 composed of, right? So this so let me just clear this stuff a little bit. So this v2, right, is composed of this purple line and this purple line, right? So that's essentially a sum of the x green line and the x blue line, and then the y green line and the y blue line, right? So that's how it is, right? So that's what vector addition is all about, right? So you're just adding vectors, right? And the way that you represent vector addition is like this. Okay, so it's called it's basically like called head to tail, because what you're doing in vector addition is basically you're taking the head of one vector, okay, which is the head of the first vector, and aligning it with the tail of the second vector. Okay, aligning with the tail of the second vector. Vector subtraction is a little different. I mean, it's the same logic, like you're just ultimately just replacing the plus sign with a minus sign. Okay, you're just replacing it minus sign. But when you actually sort of want to do it graphically, like if you want to do it on a piece of graph paper, what you do is you do something like this. You do tail to tail. You align both vectors from tail to tail, and then you look at you essentially look at you join the heads. Okay, so you do this because you can try this out on your own. You can just look at like two vectors. You can pick up a grid paper and just play around with this, right? You can look at two vectors. You can align both of them tail to tail, and then you can essentially just look at that difference. So that's what it is, because if you align them head to tail, right, that's going to be addition, right? So you have to align them tail to tail for you to get that difference. Okay, so this vector here represents v1 minus v2. This vector here represents v1 plus v2. So again, like all of these vector operations are pretty straightforward. Like you just play around with them. So my suggestion would be pick up the data set, pick up any data set from sklearn or any other data set that you find, and think of those points as vectors, and then just start playing around with them in Python, right? like start adding them, start subtracting them, see what you get. Okay, start getting the magnitude out of it, and so on, right? So that's something worthwhile. That's a good activity to play around with. Okay. All right. So that's vector. Okay. So okay, I shouldn't have stopped broadcasting because the next one. So we covered vector addition and we covered vector subtraction. The next thing that we need to cover, the next part is a little messy. Okay, so you're going to have to sort of pay a little more attention on this one. So we can actually also multiply vectors, and we can divide vectors. Okay, so far with vectors, we have done addition, right? And we have done subtraction, right? Next, we'll do multiplication, but there's no division. At least not in the sense that you divide numbers. Okay, not in the same way that you divide like standard numbers. So there's no sort of notion. I mean, at sort of some advanced level, there is that notion, but there's no real notion of division in a vector. Okay, so the first sort of multiplication. So there's two types of multiplications when it comes to vectors. Okay, so there is something called a dot product, and there's something called a cross product. Okay, so what these both of these are extremely important because there's so much that you can just do with both like the dot product and the cross product. It can be like super useful. Okay, so the dot product essentially gives you a scalar. Okay, the cross product essentially gives you a vector. Okay, so that's why there are two different types of multiplications. Okay, and so the dot product is extremely heavily used. Like so basically, if you want to okay, so let me first define it, and then what we can do is like we can talk about like why it's heavily used. So the basic idea of a dot product is that if I have a vector, okay, so if I have vector 1, if I have vector 2, so what I can do is I'm just doing A1 times B1, A2 times B2. And this number, this quantity here is the dot product. Okay, you're just multiplying each of these elements individually. Okay, so what's weird here? So you should be asking or thinking about the question, why did I write this like this, right? So why did I write horizontal brackets and then vertical brackets, right? Why isn't this, right? Why isn't it like this? Right, so anywhere you go and look up dot product or cross product, you're going to find that this notation will be in such a way. Okay, that's because there's something called the idea of a row vector and a column vector. Okay, so a row vector is nothing more than when you have something like this, like it's flat. Okay, so when you have a horizontal vector, you call it a row vector. So you can do there's an operation called transpose. You write a little t. So when you write a transpose, it becomes a column vector. Okay, and transpose is going to come in like in a very serious way when we talk about matrices. Okay, but the basic idea is, so when you have a1, a2, you have a row vector, and when you transpose it, it becomes a column vector. So in here, we actually start with a column vector. If I transpose it, you have a row vector. So what column vectors and row vectors represent are essentially like how like how you represent your vector components. That's all they represent. There is, at least in this context, there isn't an easy geometric example that I can give. I'll think of something and I'll come back with it. But just keep in mind that, so whenever I'm writing it flat, it's a row vector. Whenever we're writing it vertical, it's a column vector. Okay. So the other thing is you cannot multiply a row vector with a, you can multiply a row vector with a row vector, a column vector with a column vector, but that, that's not how dot product works. For a dot product, you must have a row vector multiplied with a column vector. Okay, so now here comes a fun trick question. How do I take the dot product of this? Can anyone answer? What would I write here?
I don't think that's possible, is it?
Yep, you're right. Because I would write this, I would write this, but then what do I write here? I don't have anything else to multiply it with, right? So basically, the length of this vector has to be equal to the length of this vector. Okay. So for dot product, the condition is that the length of a1, a2, so has to be equal to the length of, okay, so length of A vector must be equal to length of B vector. Otherwise, you cannot take a dot product. You could add some zeros here and take the dot product, but that doesn't truly represent the correct situation because you don't know what these values are. Okay, but you need these lengths to be equal in order to take the dot product. Okay, there's another alternate definition of the dot product. Okay, so this is I mean, it's a similar definition. This is one definition. The other definition of a dot product is if you have two vectors a dot b, we actually, it's an equivalent definition. So this is the magnitude of A, this is the magnitude of B, and you use something, so this is called cosine of theta. Theta is the angle between the vectors. So the sort of the best way to visualize this is, so let me just do that again. So I got A dot B, which is equal to A, B. You guys can see my screen, right? Hello?
Yes.
Yes. Okay. I was not sure. Okay. So you have A dot B, right? So this is cosine theta. Okay. So basically what this tells you is if you have two vectors, A and B, okay, so this angle is, so this is this angle, okay, so so suppose this is A, this is B, right? So why is this definition super important? Because what you can do is you can calculate this angle theta, okay, and so you can use cosine inverse, and then you can do theta B divided by. So this theta becomes a measure. So if you have 2 points, right, which your vector is pointing to, right, you can use theta to measure how close they are. Okay, so this is called cosine distance, and this is heavily used in data science and machine learning all the time. Okay, this idea of cosine distance. So so suppose if you do natural language processing, right? So what happens is in natural language processing, for instance, you have words, right? So suppose I have the word I am a duck, okay, I am a truck, right? So how do you say that these two sentences are similar, right? So how do you say that sentence 1 and sentence 2 are similar? So what you do is for every word, okay, you generate a vector. So this will have a vector representation of x1 all the way till x100. You know, am will have a vector representation of x1, you know, so let's call this x21 all the way till x200. Then A will have a vector representation of x3 all the way till x300. Okay, and so on. So for each this, and what you do is you take the average of all these vectors. Okay, so you'll get some x average. Okay, and so that's for sentence 1, right? You do the same thing for sentence 2, and when you have, so you know, if we boil this down to 2-dimensional space, so for each sentence, right? For sentence 1 you have a vector, and for sentence 2 you have a vector. You essentially like measure this distance, you calculate that cosine angle, and when you do that, you essentially, you know, figure out how close you are. So suppose you have these 2 sentences, and you have a third sentence that me writing this sentence, right? So what's going to happen is that if I have that third sentence, my third sentence might, so I might have a situation where, you know, this is sentence 1, this is sentence 2, and my third sentence might be like this, right? So so the cosine distance between sentence 1 and sentence 2 is small, whereas the cosine distance between sentence 1 and sentence 3 is large, and the cosine distance between sentence 2 and sentence 3 is also very large, right? So this basically goes to show that sentence 1 and sentence 2 are close by. Okay, you can do this with words as well. So in again, like so if I look at duck truck, right? If I look at the space, if this is my word duck, if this is my word truck, these are going to be close by, because if you look at the 3 sentences that I have, I am a duck, I am a truck, like because these letters are similar, that's why the word duck and truck are followed by these letters, right? So since that relationship exists between the words before the word duck and the words before the words truck, since they're exactly the same, there's a relationship between these words in this data set. Whereas the word sentence or writing will be somewhere else. The word sentence or writing would be somewhere else, right? So the word writing will be here, sentence would be here, or something like that, right? So these two words are going to be similar. So that's where, like, that's why understanding something like cosine, like the dot product, is very important. Like, this is an application of this idea or this definition of dot product. Any questions for this? So this is the dot product. So I'll move on to the next one. So the next one is the cross product. Okay, and the cross product is really, really messy. So I'm not going to go super into detail, but so what the dot product is giving you is it's giving you a scalar, right? So it's giving you one value. It's giving you a single value. The cross product gives you a vector. Okay, so you don't need to know how it's calculated, but what you need to understand is what it actually signifies. So the cross product essentially is given by so the actual calculation of how the cross product is done is like really, really long. But the basic idea of the cross product is, suppose I have two vectors, okay? So and the cross product really only works in 3D, okay? You can't really do a cross product in 2D. So suppose I have my x and y here, okay? So I have a vector. So this is where colors are super useful. So I have a vector like this. I have a vector like this. Okay. So the cross product is actually going to give me a vector in the in the z direction. Okay. So this vector is in the xy plane. Okay. This vector, the blue vector, lies in the xy plane. The green vector also lies in the xy plane, but this vector here, which is my a cross b, it actually lies in the z plane. Okay, so that's what the cross product is. Okay, and NumPy gives you a simple way of calculating this. I'm not going to go over the calculation. It's really, it'll just be really messy. We've given the calculation to you in refactored. Again, like NumPy gives you, since it gives you that easy way of doing that, it's worthwhile just checking that out. But it basically will give you a vector. The basic idea is that anytime you do a cross product, right, any plane that you define, the cross product will always be perpendicular to the plane that's formed by these two vectors. So the idea is, if I had another situation where my first vector was like this, and my second vector was like this, right? Then my third vector would be like this. Okay, so this is my x, this is my y, this is my z. So my first vector is so in this case, what's happening is that my blue vector is in the xy plane, right? Then my green vector is actually in the xz plane. Okay, so it's in x and z, right? So if you collapse y, that's what it's in. So my purple vector is going to be in the, so so it's basically going to be perpendicular to that. It's going to be in the XY plane. Okay. Does that make sense?
What is the purple plane perpendicular to? I didn't get that.
It's perpendicular to the plane defined by your green and blue vector. So think of it like this. Your x. So okay, very simply put, your XYZ is actually a cross product. Okay, so your XY dimensions form a plane. Okay, your Z is just a cross product of X and Y. Okay, and this angle here is 90 degrees, right? So if you take the XZ plane, right? So if you take, so let me give these different colors. It's just easier. So let's say, so my XY plane is this direction. Okay, this is my XY plane. So my purple vector here represents my cross product, right? So if I just take my XY plane, my cross product is in the Z direction. If I take another plane, right? So let me pick another plane. So if I take, for this, I need to draw another grid. So let me pick this plane, right? So this plane is X, Y, Z, right? So this is the ZY plane, right? Or ideally speaking, you should write the YZ plane, right? So this is the YZ plane. Then my cross product will be in the X direction. It'll be in this direction. It's essentially perpendicular to the plane where your vectors lie, right? So if your vectors lie, so it's always like this. It's actually called the right-hand rule. So whenever you get confused, like, so suppose, like, look at these two vectors, right? These two vectors are essentially pointing in some random direction. So where is my cross product going to be? It's going to be perpendicular to them. Okay. If you're pointing in some weird direction, it's going to be perpendicular, right? So and essentially, like, you can have vectors point in any direction, right? But there's a plane that's defined by them. See, if you have two vectors, so if you have just one vector, right? The one vector is kind of like a line. It's pointing in some direction. You don't have a plane, right? But if you add a second vector, right? You essentially, like, you can define a plane, right? So for instance, here, right? So if I take X, Y, Z, right? I can essentially define a plane by taking two vectors, right? So if I take some random vector in some direction and some another random vector in some direction, I can actually define, like, I can say that these two define a plane, okay? And then my Z, right? Any vector perpendicular to this, right? Any vector perpendicular to this, that's where my cross product will be. Okay, so it's much easier to sort of see it in 3D, but the basic idea is this, that the cross product will give me a vector in the perpendicular direction. Okay, the cross product isn't, like, it's used to conceptually understand certain points, but it's not as heavily used in machine learning. But there's a very important conceptual point it makes, is that, you know, it helps you understand, like, geometry, right? How, you know, see, because ultimately these vectors are data points that from your data set, right? So it helps you understand, like, okay, if I take the cross products product of these two sort of rows of data, what am I going to get, right? I'm going to get some vector which is pointing in the sort of perpendicular direction, right? And that information is useful to me in some way or the other, right? I can do something with that, and there are certain machine learning algorithms that actually do use that information, but it's not something that's as explicitly used. Like the cosine, sort of the cosine distance is very heavily used, like especially in NLP, and in many other use cases, like even with just tabular data, not just natural language processing or words. Like this idea of cosine distance is very, very heavily used. It's very useful because you when you want to look at like the distance between points, the cosine distance is a much better distance to calculate rather than just a simple distance, because it's just one number. And so the benefit of cosine distance is because it goes from it's a bounded number, like because this number theta can only go between 0 and 360, because you can have theta that's 0, or you can go all the way around and then end up at 360, right? Technically it's the other way around. Right, so there's a bound here, so between 0 and 360. But if you look at two points, that distance can be however large you want, right? It can be as large as you want it to be, and it can become like there's no bound to it. There's no upper bound or there's no lower bound to it. Here there's a lower bound of 0, there's an upper bound of 360, and you can adjust these bounds by subtracting values. You can adjust this bound to be between 0 and 90 or 0 and 180, something like that. So you can adjust these bounds, whereas you cannot do that with distance between 2 points, because they can be as large as they want, they can be as small as they want. That's why the cosine distance is very, very heavily used. Okay. All right, so that's vector operations for you. So that's 2 notebooks that you guys can go and read about. Let's actually play around with vectors on the data set, right? So we've sort of looked at like we've looked at mathematically like what that means, what that looks, how that looks, but let's actually do this with an actual data set, right? So we have this data set here, right? So can someone tell me how can I get a row of data from this data set from DF? Like, what do I have to write to get just a row of data from this?
Dot head.
Dot head. So let's call this V1. Right. So you're saying dot head. Head. What do I have to input?
I don't remember the syntax very well.
So the best way to check that is so you can do this. Whoops, that's not what I wanted to do. Okay, so sorry, not index. iloc. So this is one way of getting the first row, right? So this is the first row. Okay, and this can be any row. Okay, so this is V1, and let's just get like say the 10th row, right? So how would I get the 10th row? it is a bit of a trick question. How would I get the 10th row? What would I type? Yes, 9 and yep. So you type 9 and this, because in Python you are indexing from 0, right? So we have these two vectors, right? So we have v1 and then we have v2, right? So what I'm going to do is, so right now these are not numpy arrays, right? So these are not numpy arrays. These are panda series, right? Because I'm just splicing the data frame. So so how do I get just the values? I just want the values. I don't want the column names, right? Because I know there's like 7 columns, so the vector is going to be 7 columns long. So how do I get that from v1? Any guesses? So it's using values. Okay. So if you just, so in this case, what I'm doing is I have v1. So I should just call this v1 array. Okay. So and then I have v2. So I got v2 array values, right? So this is how I get my values. So I got my v1, which is a numpy array, and I got my v2, which is another numpy array, right? So now that we have both of them, right? So vector addition and subtraction is pretty simple, right? So vector add is literally just v1 add v2, right? It literally is just that, right? So this vector is essentially a sum of vector 1 and 2, right? So nothing fancy there. Vector subtraction would also be pretty simple, right? I'm just subtracting elements. Although the mistake I made here was I should be subtracting the first one from the second one. So the second one from the first one. That's how it's usually done. Okay. So you always start with the second vector and subtract the first one. So it's yeah, that's how it's usually done. So now what about dot product? Like, how do I calculate the dot product? So there's two ways of doing that, right? So one way of doing that is I can just use np dot dot, and then I can do so I can do v2 array, v1 array, right? And v dot 1. I'm just going to call it v dot 1. V dot 1, right? So that's the dot product. That's sort of the value. Okay. So that's what you get when you do multiply each element with each other and then sum all the elements, right? So the question I have for you is, so here I've done v2 with v1. I've multiplied v2 with v1. What happens if I multiply v1 with v2? So with respect to the answer in v1, like v dot 1, like what would it be? Should it be different or should it be the same? What is it and why? Can somebody answer that? It should be same. Mari says it's same. So Mari, why should it be the same?
I believe it's the same vice versa. So
it's because the order doesn't matter in multiplication, right?
Yeah.
So when you multiply 2 times 3, it's the same thing as multiplying 3 times 2, right? So that's a property of multiplication. So from that context, it's really, really useful to have that. Okay, so that's useful for us, right? So that in that sense, it's good to have good to understand that. So v dot 2 should be the same value, right, down to the closest decimal, right? So there shouldn't be any difference. Okay, so in order to do some of the other things, right, like to calculate, so this you can see is the dot product. So for cosine distance, there's actually a function in sklearn to do this. Cosine, it's called cosine similarity or cosine distance. So it's called pairwise. So one thing that you guys have to, all of you people will have to know how to do is read documentation, because many times I'm going to refer you to certain places where I'll want you to go and like look up something, and reading documentation is really important, especially sklearn documentation. Like it's fairly organized in a straightforward manner. What it tells you is it gives you the function, it gives you the inputs for the function, and the parameters are essentially the inputs for the function, and the returns is like what is it actually returning. Okay, so this information is always here. So make sure that you learn, like just go through this and like learn how to read documentation, right? So in this case, you have cosine similarity, so here you give your vector x, you give your vector y, and then you'll just get a kernel matrix essentially. So it can, so this actually this will not give you the value. So wait, cosine distance is what I have to search for, not similarity. Right, so pairwise cosine distance, right? So this will give you the actual value. Okay, so there's also a SciPy version of it where you can get the value. So for example, let's try this. Oh no, but this is just cosine distance between, so that's the one that I was looking for. So for this, you just do import, and then what you do is you just do distance dot cosine, and then you do v1 array, v2 array, and it'll give you the distance. Okay, so you can see the point here, right? Like if you just use the dot product, like the raw value, you're gonna get such a large number, right? And if I just look at the distance between these two vectors, right? So if I just look at the Euclidean distance, so the Euclidean distance is nothing more than the distance that I calculate between those 2 points is a straight line distance. Okay, the Euclidean distance. You can see that the Euclidean distance is very large, right? It's 1,200, and it keeps increasing as the points go far apart, right? So I can pick some other point as well, and it'll just keep increasing. Whereas if I look at the actual cosine distance, the cosine distance will remain bounded, right? So it'll remain bounded between 0 and something else. So that's something useful to sort of keep in mind when we're talking about vectors, right? So cosine distances are useful, Euclidean distances are useful, but they're not always preferred because it's just easier to think in terms of, in terms of like cosine distances rather than Euclidean distances. Okay, so that's an important point. Yeah, go through the content. You'll, once you start like doing the lab, also you'll have more questions. The lab isn't necessarily trivial for this one. It is a more complicated lab compared to the previous one. So I do not expect that it'll be a breeze. So that's good. So what we'll do is we'll cover introduction to matrices, and then we'll stop for the day, and then we'll cover the rest of it next Wednesday. Okay. So I'll give you sort of a general idea of matrices, and then next class we'll go into like special matrices and what those are. Okay. So yeah, so let's start with this stuff. So have any of you do any of you remember anything about what a matrix is? Yes, no. Have you ever heard of the word, except for the movie?
Yes.
Hey, James, you have definitely heard of it. All right. So let me sort of so I'll switch to my iPad for matrices. It's much easier. So let's see. Right. So far we covered vectors, right? So in vectors we were just like looking at essentially like columns, like rows as essentially vectors, right? Now the thing is that when we were looking at vectors, we just looked at single rows or columns of data, right? So if you took a row of data, you have x1, x2, x3, all the way till xn, right? So n can be any number. N can be 100, n can be 1,000, it can be any number, right? It doesn't matter. So we just denote it as xn, right? So now when you're looking at like the idea of a matrix, right? So this is one representation. So we have the way there's a hierarchy here. So the way that it works is scalar is the simplest representation where you have a single value. A vector is a more complicated representation where you have you know, sort of n times 1. So we call this an n times 1 entity, okay? Which means that, or this would actually be a 1 cross n because I have n values and I have just one column, right? So a matrix is essentially when you combine like multiple vectors together, okay? So you just put multiple vectors together, and what you're gonna get is you're gonna get a matrix. So you're gonna have something like this, dot, 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 x1n, x21, x22, x2n, x, and then dot, 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 you know, n1, x, n2, x, and n. Okay, so this is an example of a matrix, right? So think of it like this: a vector can be some number 2, a matrix would be some number like 3, 2, and you know, vector would be, sorry, a scalar is the number 2, vector is 3, 2. You'll have something like 3, 2, 3, 2. Like this is a matrix, right? So the idea of a matrix actually emerged from a, you know, very different avenue. The idea of a matrix was that so matrices actually emerged when people started thinking about how to rotate vectors in space. Okay, so suppose I have a vector like this. Okay, so I have this vector here. Okay, it has the component vx and it has the component vy. Okay, and this is the vector v. Now suppose I want to take this vector and I want to rotate it, okay, to here. So mathematically, the way that you would do it is, so this new vector is actually v dash. So mathematically, what you would do is you have a rotation matrix, okay? And this rotation matrix would take, it would take your vector v to v dash, okay? And that's where this comes. So why do you need a matrix for that, right? Because the reason you need a matrix for that is essentially what's happening is your v here essentially has two components. It's got x dash and y dash, okay? And what you have to do is you have to multiply your vector x, y here, right, with I'm just going to call this R11, R12. I'm not going to tell you what actually R would be, but I have to multiply it with this object here, okay? So what's going to happen is that my x dash, right, is nothing more than R1. So I'm essentially multiplying. So let me do this. R1 x plus R12 y. That's what this is, okay? And the same thing for y, okay? That's why you need matrices, because if you want to multiply values, right? If you want to rotate vectors, if you want to do anything to a vector, you're gonna need the structure called a matrix, okay? That helps you essentially do these operations. Okay, so and so you can imagine this in the context of data, right? So like when you're adding and subtracting, you don't really need anything, right? But you can also represent like that addition and subtraction in terms of a matrix. Like if you want to, you can do that, right? But the idea is that you don't really need to worry about it when you're doing adding and subtracting. But if you want to rotate a matrix, if you want to rotate a vector, if you want to scale a vector, right? So if you have a vector like this, you want to make it longer, you just multiply the components, so you don't have to worry about it. But if you want to sort of move it horizontally, right? So this is called a transformation, okay? And there's like many different types of transformations that you can do. Like rotation is just one transformation. Like the other transformation is like reflection, right? So if you have a vector like this, you can reflect it in the opposite direction, right? So that's also a transformation. There's like shear, which is like you move the vector in just this direction along this line, right? So that's another sort of example of transformation. So there's different types of transformations that you can do. And essentially what a matrix allows you to do is it allows you to do these sorts of transformations. And that's where matrices really come from, right? And that's where matrices are very, very useful. But another way of sort of thinking about matrices is your data set is also kind of like a matrix. So if you look at it from the point of view of row and column, right? So your data set has row 1, 2, 3, 4, 5, 6, and so on. It has columns 1, 2, 3, 4, 5, 6, and so on, right? So your data set is nothing more than a giant matrix, right? So if I have a data set with 10 rows, say 20 rows and 10 columns, I essentially have a matrix where I have like 10 rows and 20 columns. 20 rows and 10 columns, right? So I essentially can think of it like a giant matrix, right? And that's sort of one way to think about it, right? But the main idea, the main use case of a matrix is really to think about it in terms of rotations, in terms of any other sorts of transformations that you can do to a vector. Okay, mathematically, that's the most sort of accurate way of thinking about it, right? So matrices are super prevalent, especially when you start thinking about like what can you do to a vector. And a lot of sort of machine learning algorithms, you'll find that matrices are very useful. And when you're thinking about data in general, like it's pretty useful. So, so what you know, how do we sort of think about a matrix, right? So each row of the matrix can be considered a vector. Each column can be considered a vector, right? So if I have x1, x, so typically when you write a matrix, the elements of a matrix, you write them with a subscript. So x11 basically means this is row 1, column 1, right? So x12 means this is row 1, so this is row 1, column 2. Okay, x13 means row 1, column 3. X1n means row 1, column n, right? And then you will have like x21, and then you'll have xn1, right? And then you'll have xnn here in the corner, and then you'll have whatever those points are. Okay. So, so if I write down a 2x2 matrix, it would be x11, x12, x21, x22. If I write a 2x3 matrix, so I have x11, x12, x13, x21, x22, x23. Okay, so this is a 2x3 matrix. Okay, and there's a 2x2 matrix. Okay, so that number, the first number represents the number of rows, the second number represents the number of columns, right? So this is very simply called a square matrix. Okay, so anytime you have an n cross n matrix, can be a 6x6, can be a 10x10, can be a 1000x1000, called a square matrix. Because the number of columns is equal to the number of rows, right? So that becomes important. So there's a whole bunch of like matrix operations that are worth going over. Okay, so before I go to that, any questions with this as to how we're defining this matrix? Like any questions with this? Yes, no, completely confused, extremely exhausted. Esther, you're getting everything?
I probably will get when I look at the notebook. I don't know.
Do you guys want me to stop here so that you don't get overloaded? Do you
Yes,
guys
please.
want me to? Okay. What about the others?
I agree. I just haven't, I only went halfway through all of these lessons. So I have a hard time,
Okay. So I'll, in that case, I'll stop for now. What I suggest everyone does is for next class is next Wednesday. Okay. So you have an entire week. Please read everything. Okay. Read the entire section on linear algebra. Okay. You're not going to understand all of it in the first go. It's perfectly fine. Just read through it. So one thing I'm going to suggest you guys do is, okay, so let me stop sharing screen here. Let's share my screen here. So everything that I was teaching you here, right? So if you, and most likely you will find all of this fairly confusing, right? When you read through it, I very, very highly recommend going to YouTube, going to 3 blue, 1 brown, okay? Okay, and so so watch this first chapter, okay? So I'm going to share this link with you. Please watch this, okay? Because this guy's explanations on this stuff is mind-blowing, and he has really, really good visualizations, okay? So one thing I didn't talk about like was how you move vectors around, you know? So like, you know, when you take a vector, you can just basically like move it around in whatever direction, and it doesn't really matter. It doesn't change the vector. It's pointing in the same direction. The length of the vector is the same, right? So he'll talk about that as well, but he'll talk about, you know, he'll show like interesting visualizations, and what you can do is you can come back, you know, you can come back, and then we can really discuss this and figure out, like, if you don't understand something, we can really cover that, right? So that's something that's very, very useful. Okay, so he does a really like good job of, like, some things are a little mathematically inaccurate, but you know, he does a really good job of explaining like what a vector is, and he also has a section on what matrices are. Okay, so I would highly recommend just going through his videos. Okay, so yeah, please go through his channel and just start looking at these videos. Okay. He covers matrices when he starts talking about linear transformations. Okay, and it's the same example that I was giving. You know, so it's the same idea. Like, you have a matrix that you multiply with a vector, and that's when you get another vector, which essentially represents some operation on that vector. Okay. So he covers all of it. I'll make you watch this specific video once we cover matrices. But if you want, go ahead, watch this video as well. It's on linear transformations, chapter 3. You can watch chapter 2 as well. But it's super useful to watch these videos. Okay. Yes, no, all right.
Yes.
Yes, okay. You know, you guys can ask questions, right? So don't shy away from asking questions. Hubert, can you send them that link that I shared?
Okay.
Yeah, just send that link to them, because I think it's super useful for them to just go through the link. I think it'll really help.
The YouTube video, right?
Yeah, the YouTube video. Yeah.
Okay.
Yeah. So this is a great channel if you want to understand how to think about geometry and linear algebra, you know, and it becomes like super important, especially like the last notebook that we have in this section is on eigenvectors and eigenvalues, and his explanation of eigenvectors and eigenvalues are like, they're kind of like an inspiration that I draw from, because he really explains it very well. Like, you know, there are other people who do this as well, but it's always good to, you know, good to go through that. So when you're thinking about these things, it's important to work it out by hand. So also make sure that you just work it out on a piece of paper, like what, so watch a video and, you know, then shut it off and then try to do it by yourself. You know, try to think about, okay, what are the words he's saying? Like, what do I write down? Right? Like, so think about it from that point of view. That's how you'll learn. Okay, so don't just watch a video and forget about it. Watch it, turn it off, and can I reproduce everything that he said on a piece of paper? Right? Does it make sense? right? So that's the way to go about learning this stuff. All right, okay, guys. So I'll close the class for today at this point. We'll catch up next Wednesday, and yeah, awesome. Good job, everyone. You survived most of the class. So
Thank
yeah.
you.
Take care.